spectrometry. So the first thing this is asking us is to explain how a mass spectrometer, right? So that's the instrument that we use to do mass spectrometry, right? So this is our instrument. And they want us to explain how this works to obtain a mass spectrum of a molecule, right? So let me just give you guys a run through of the steps, right? So let me just write that like this. I'm going to write it in a stepwise fashion, how we do this. So we have a sample, right? And we want to put it in the mass spec machine so that the mass spectrometer will give us ultimately a mass spectrum. And from that, we'll be able to determine the atomic mass of the atoms or molecules in that sample. Okay? So let me just give you a rundown on that, on the steps needed to do such a analysis, right? So the first thing that we're gonna do is that we're gonna take our sample, right? Take sample and vaporize it. So whatever my sample is, if I have a solid sample, I'm gonna put it in a vapor form. So I'm gonna vaporize it. If I have a liquid sample, I'm also gonna vaporize it, right? Once I'm in that vapor phase now, what I can do, or what the spectrometer, what that machine does, right, is that it ionizes. So the second step is the ionization of the sample, right? And so the way that the mass spec machine does this is that it uses high energy electrons from what we call a heated cathode. To knock out, right? To knock out one or more electrons from our vaporized sample of atoms, right? So just to see where we are now, so first we take our sample and we vaporize it, we put it in the vapor phase. Then now the next step is ionization of the sample. And inside of the mass spec, there is a heated cathode, and that provides some high energy electrons, and you're gonna just bombard your vaporized sample with those high energy electrons, and that will knock out one or more of the electrons from our vaporized sample, and then it will form positive ions, right? So this will form, right, positive ions, right? Because we knocked out an electron, so it has a net positive charge now. So we form a positive ion. The third thing that's gonna happen inside of this mass spectrometer, this instrument, is that the positive ions, right, that we just created from that ionization step are then, those positive ions are then accelerated using a negative plate, right? A negatively charged plate, because opposites are gonna attract, guys. We have a positive ion. So if we use a negatively charged plate that's positioned in our spectrometer, so that negatively charged plate is actually acting as like an electric field, right? So we're able to then accelerate the positive ions that we made from step 2 using this negatively charged plate. And then now one of the next steps, not the final one, but the next one is that a magnetic field that's inside the mass spectrometer, a magnetic field within the machine, so the mass spectrometer, will deflect, right? So now it's going to deflect or bend, right, our positively charged ion that we generated and accelerated, right? It's going to deflect it towards a detector screen, right? It's going to it's gonna deflect, it's gonna bend it, the magnetic field is gonna bend the positively charged ion in such a way that it goes towards a detector screen, right? And then now finally, we will then see what the detector picked up in the form of a mass spectrum, right? So those are our 5 steps to go from sample to mass spectrum using a mass spectrometer. So the mass spectrum that the detector pick up and give us so we can see is gonna look something like this. We have this, this X, this is our Y-axis, this is our X-axis, and on the Y-axis, we'll see percentage relative abundance on our Y-axis. And then what we get on our Z is gonna be our MZ, or our mass to charge ratio. So that's just gonna tell us the mass of the ion compared to the charge on it, right? So that's why we had to give it a charge first. We ionized it, so it has a charge on it. If it lost 1 electron, right, then the Z would be +1. When we ionize it, it lost 1 electron, the Z would be +1. If it lost 2, then the Z would be +2. And then of course the mass is just the mass of that ion, right? So the M to Z ratio is what the spectrum readout gives us, and the relative abundance of that particular species that's at that MZ ratio, or that ion. So you see something that looks like this, bam, 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 right? You might see something that looks like that. So that's kind of what your mass spectrum will look like. It will give you the relative abundance at a specific MZ ratio, okay? So just to recap the steps, guys, we are going to take our sample and vaporize it, right? So that's our very first step. Take your sample, vaporize it. We're making it gaseous. So if we have a solid, we're going to make it a gas. If we have a liquid, we're going to make it a gas. Then we're going to ionize that sample, and the compartment that does that ionization within the spectrometer is the heated cathode. And what that does is it supplies these high energy electrons, which knock out 1 or more electrons from our sample, from our vaporized sample, right? And then this will form positive ions, because of course, when you lose an electron, you're going to end up having a positive charge. So this step is to form positive ions. That's the purpose of this step, right? So then after we form our positive ions now, then we're gonna accelerate them, so speed them up, right? Within the mass spec, using a negatively charged plate or electric field, right? So we speed them up, so that's acceleration step. Then we're gonna deflect it using a magnetic field, so bend it, right, towards a detector screen. And of course, you know that particles that have a higher mass are going to be deflected less, and particles that are light are going to be deflected more, right? So the lighter you are, the more deflected you'll be. Heavier, less to deflect. So just keep that in mind. And then now, finally, right, after we deflect or bend the positively charged ion to the detector screen, we will then see what that detector was able to pick up, and in the form of a mass spectrum. And the mass spectrum looks like this: percentage relative abundance versus MZ ratio. Okay, guys? Does that explanation of how a mass spec works make sense to you?
Yes, Miss.
Desiree, how about you?
Yes, Miss.
Okay, so let's clear this and move on to the next question. So now we're at the spectrum, right? So here they're showing us the mass spectrum of a haloalkane. So we know there's a halogen in here somewhere, right? A halogen atom. So right away, I'm gonna write a halogen atom is present in this haloalkane. That's what they are. They have a halogen atom in there. And so the spectrum is representative of that, whatever that haloalkane is, right? All right. So now, when we look at a mass spectrum, right, we get a readout of a mass spectrum, and we're looking at it, we see that we have all these ranges of M to Z ratios, and we have a relative abundance over here, right? So that's what the mass spectrometer is going to give us. So we get this spectrum. Now, we have what we call a molecular ion peak, right? That's our M plus peak. So that's our molecular ion peak, right? And that is the peak that's associated with that ionization of the molecule or the sample that we put in, right? So that molecular ion peak represents the 1 electron being knocked out of our sample, right? So the ionization of the sample is what produced that. So typically when we're looking for the molecular ion peak, we're generally, let's just veer far to the right, right? And look for a mass that's way out here. That would be associated with our molecular ion peak. So when we have our whole molecule, our whole sample, and we just knock off an electron to ionize it, that would be our molecular ion peak. So we're gonna look in this region here, right? So for intents and purposes of this, for this spectrum, our molecular ion peak will be this one right here, right? So this will be our M plus peak. So the M plus peak is at a MZ ratio of 122, and that's what they want us to write here, right? So this is our molecular ion peak. And then now we have this, they're asking us about an M plus 2 peak. So M plus 2 peak, it's not a M2 plus peak, it's a M plus 2. So it's whatever the MZ ratio is of our molecular ion peak plus 2. So that would be at 124. That's where the M plus 2 peak would be. It's 2 more in mass than what our molecular ion peak is. And so if we look here, we see that that's represented by this line here. Do you guys see that? This line here, that's 2 units away from our M plus, would be our M plus 2, right? It's two mass units heavier than the M plus, and that is around 124, right? So right away, we've answered this first part, so part I, right? So then now, what I also wanted to point out here is that we can get some very useful information from the M plus 2 peak, right? So the M plus 2 peak generally arises when we have isotopes, right? So if there are isotopes within our molecule, atoms with isotopes within our molecule, we'll get an M plus 2 peak, right? So we can get an M plus 2 peak from chlorine, because we have chlorine existing as Cl35, and we have it existing as Cl37, right? So we have 2 isotopes, and what you'll see right away is that there are 2, the difference between them in mass number is 2, right? So that's why we would say that M plus 2, because this one would have the chlorine that's lower in number, and then this peak would represent an ion that has the chlorine that's 37. So that's why it's M plus 2. Does that M plus 2 stuff make sense to you guys?
Yes, miss.
Okay, so the other thing I want to say is that we can also have bromine giving us an M plus 2. That's another halogen, bromine, right? So when bromine forms isotopes, it's gonna be a 79 bromine and an 81 bromine, right? And in terms of relative abundances, these are in the amounts of 50.5%. The 79 would be 50.5% abundant, and the 81 version of the bromine would be, what's the remainder there? 49.5, right? So you see that they're fairly close in their abundance. So we have 50.5% for 79 bromine. So that's the one that would be at our molecular ion peak. And then the plus 2, the M plus 2 peak, would be indicative of the 81 bromine being present, and that would be 49.5% in terms of its relative abundance. So that's very close, right? So when you look at this diagram now, what you see is that in terms of the relative abundances listed here, right, they're fairly close to each other. So 50.5, 49.5, they're fairly close to each other, right? So we can venture to say that the particular halogen that's in this alkane is bromine. So we can make that deduction right away by looking at our spectrum, right? So based on these two peaks and their relative abundances, we can say that our bromine is the halogen that's present, right? So Br is present. Present. So we were able to reduce that based on relative abundance, right? And just looking at those, the M plus peak and the M plus 2 peak, right? If it was chlorine, guys, what you would see, because the chlorine 35, right? This one is what? What percentage is chlorine? Is 35? 35.5? Well, what percent is 30 of the isotope is 35 chlorine, and what percentage is 37? Do you guys remember? For chlorine, in the case of chlorine, right, this one is actually 75%, right? And then, so I guess 75.5 or 74.5, sorry. So it would be 74.5%. And then the 37 would be 24.5%. So you see that if this were chlorine, guys, what we would expect on the spectrum, what we'd expect to see is that these two bars, so the relative abundance of the M plus to the M plus 2 would be significantly less, right? For our M plus 2, because 74% would be in the M plus peak. So this bar would be, so this is 75%. Then the other one would have to be around 25. So it would be about a third of it in terms of height, right? So when we look at these two, the M plus and the M plus 2, right away we can say, boom, that's not going to be chlorine because they're too close to each other. What's close to each other in terms of relative abundance? When we speak about isotopes, bromine. So we're able to zero in on bromine, right? And say, okay, I know right off the bat that my halogen or my halo atom that's present is going to be a bromine 1. Are we good up to that point, guys? Let me know.
Yes,
Yes,
Miss.
Miss.
Miss, how do we know the M plus peak is 122?
So the molecular ion peak, right? Okay, so let's look at the whole spectrum holistically, right? So from the mass spec theory, we know that we have the peak that has the highest, or we call this our base peak, the one that has this highest abundance, we call this our base peak, right? And this peak is coming from our most stable fragment, right? So it's a fragment of the entire molecule is what this would be. So the base peak is our most stable fragment. So that doesn't represent the whole molecule. So that couldn't be our M plus 1, because the M plus 1 represents our entire molecule, not a fragment of it, right? It represents our entire molecule that was ionized. That's why it's M plus, right? So we know that the M plus P couldn't be any one of these teeny tiny ones. It would have to be the one that has the highest mass, right? Because it should represent our entire molecule. And then if we look next to it, we can see that we have a characteristic M plus 2, right? There's something that's two masses away from it. And so we can kind of zero in on this region. And when we look at the relative abundances, we can see that there's some isotopy there that we can then zero in on and say, okay, this has to be our M plus peak, and then which is our molecular ion peak. And then this one would be a M plus 2, indicative of there being some isotopy. So in a nutshell, we look at the whole spectrum holistically, and we know that this is our base peak, which comes from our most stable fragment. So this can be the M plus 1 because it's not going to represent the whole molecule, and we want to get the structure of the whole molecule or the identity of the whole molecule, so we can rule out all of these down here, right? again, this looks like a fragment of some sort. And we don't see it being very abundant either. It's not, so our M plus peak is not going to be as abundant as our base peak, but it also can't be this low, right? So we can rule out this. And here again, we can see that this is a fragment. This is a fragment of our entire molecule because, again, it's fairly low in abundance. We do see a M plus 2 situation happening here, though, because there's a check mark here that's about 2 units away. So we do see that the M plus 2 feature here as well. But again, on account of the abundance being so low, we wouldn't say that this is our molecular ion peak. So what remains then is this 122 as our molecular ion peak. And then we see the characteristic M plus 2 of equal abundance. Is that clear now, Desiree?
Yes, Miss.
All right, perfect. So we're ready to move on. So, okay, I'm gonna clear all of this and then move down. And so what they're asking us now, guys, is to deduce the formula of the fragments, right? The fragments, so pieces of our entire molecule that's present at MZ ratio of 43, 107, and 109. Right? So if we had glanced down here, we would know that this is not our M plus P. This is not it. This is not it, right? These are fragments of our entire molecule, right? So this is our M plus 1 again. So let me just write that. This is our M plus, not M plus 1, M plus peak, or molecular ion peak. And this is our M plus 2. And based on our analysis of the spectrum in part I, we said that the halogen would be bromine on account of the relative abundance of the M plus 1 to the M plus 2, right? So Br atom is present, right? What else can we look at here? So we have M plus being 122, and we have M plus 2 being 124. So let me just say that this is 124. And they're asking us about the fragments at 43, and then 107 and 109, right? All right, so here's how we're gonna approach this fragmentation part of it now. So we have the molecular ion peak is 122, so that's the mass of our entire molecule, right? Our entire haloalkane is gonna be 122. The bromine atom at 122 in the molecular ion, right, would be 79. The 79 bromine, right? That's what we have at 122. MZ ratio, right, of 122. And then the 81 bromine is what we would have being present at 124 MZ ratio, right? That's just recap from part 1. All right, so here's what we're gonna do now. Let us take this mass, which is the M plus, which is the mass of our entire molecule, right? It's a molecular ion peak, so it's the mass of our entire haloalkane molecule that we know has bromine 79 in it at this point. So what we're gonna do now, guys, is we're gonna say, okay, we have our molecular ion, which is our whole molecule, right? Whole molecule. And we know that the mass of the whole molecule is 122. And we know that included in this 122 is the 79, a mass of 79 from the bromine, right? So we're gonna subtract out the mass of the bromine, which is this, right? So that's what we're gonna do. We're gonna subtract out the mass of bromine, mass of bromine atom, right? That's 79.1, and we're gonna end up with, what are we gonna get? What number is that? 122 minus 79. 122 minus 79 is gonna get us 43. Do you guys see that? So that's a MZ ratio of 43 that we're gonna look at now, which is exactly what they're asking us about, right? So they're asking us about 43, but let's go a little bit further from here. right? So if we subtract out the bromine, we're gonna, from the molecular ion, the whole molecule mass, we get 43. So what we can do next from here, or what we know from here, right, is that this 43 is gonna represent just what remains. So it's gonna represent the carbons, right, and the hydrogens, because it's a haloalkane, right? So if we subtract out the bromine, all that remains is carbon and hydrogen, right? Are you guys following me up to this point?
Yes, miss.
So we take our whole mass, we subtract out the bromine, we're all gonna be left with just carbon and hydrogen, and that is 43. When you sum up all of the masses of these, it's gonna come up to 43. So we can find out how much of this mass is accounted for by the number of carbons that are in it. So we can find the number of carbons then, right? And that's just by dividing the 43 by 12. And that will tell us how many carbons we have, right? So that would be 43 divided by 12. So that would tell us that we have roughly 3 carbons present, right? And so if we have 3 carbons, that would be a mass of 3 times 12, so that would be 36, right? So all of the carbons, the 3 carbons add up to 36, and so what remains then is 43 minus 36, and what remains will just be what hydrogen is, right? So 3 carbons, and then we're gonna have 7 hydrogens. Do you guys see that? Because what remains is what the hydrogen will be, and so hydrogen, there will be 7 of them, and there will be 3 carbons. So right away, we have a full identity of our M plus. Our M plus is C3H7, and then the Br that we took out, so it would be Br79, and this is so this is our M plus peak, so this is what we have at 122, right? So okay, so let me just draw it out now so we can fragment it or just break it up into what we want, which is what this question is asking, right? So we have C3H7Br. That's our complete thing. That's our molecule, right? Our molecular ion. This is corresponding to our molecular ion peak. So do you guys follow me to this point? How we're able to get the whole structure?
Yes, miss.
All right. Desiree, are you good?
Yes, miss.
All right. So we're here now, guys, right? We're here, and of course this is 79 because this was our molecular ion peak, and that's the corresponds to the 79 bromine. So they're asking us about the fragment at 43 MZ ratio. So this one that's right here, right? This 43, this base peak or most stable fragment. What is that? What is the formula for that fragment? So that formula would be, right? If we break this, we're not gonna have our BR in it, right? So it's when we took out the BR that we got 43, right? Remember that? When we took out our BR from it, we got 43. So let's just take out our BR. And so our fragment at 43, then the one that weighs 43 will be when we take out the 79 BR. So it will be C3, right? H7 plus. Do you guys see that? So 3 times 12, 36, 36 plus 7, 43. So that's what this 43 fragment is. Okay, guys, do you see that?
Yes, miss.
All right. So we got that one. So let's look at the 107, right? Like, how could we fragment this molecule to get a MZ ratio of 107? Well, 107, if it's 107, we're gonna have to have our bromine in there at some level and break off something else, right? So let's see where we can break this to get 107. So if we're to get 107, that means that we would have to take out a 15, a part of this molecule that weighs 15, that has a mass of 15, and that's our methyl group. So we're gonna break it here, guys, and take off this. And so this fragment, right, will be, let me just draw the arrow and write it over here. So this fragment will end up being where we break it off here, take off this methyl group, and then we have C2. So we're gonna be left with C2, H4, and then the 79 Br. Right? And so when we check up this math, we say 2 times 12, 24 plus 4, 28. Right? And then we add the 79, we get 107. So this checks out. So this is our 107 fragment. Let us box that. This is our 107 fragment, right? And what I had said earlier was that the difference, guys, between the 107 fragment and the 109 fragment is literally 2, a mass of 2. Do you guys see that? It's a mass of 2 that separates these two fragments. And so the mass, that difference can be accounted for in the fact that now what we have at our 109 MZ ratio is the bromine that is in the 81 form, okay? Because that's literally the only thing that separates this from this 107 from what's at 109. So I'm gonna come up here now and I'm gonna just draw that fragment. It's the exact same as this one, but now we have a 81 instead of 79. So let me just draw that here and show you guys. So it would be C2, H4, right? Br, 81. So that's our fragment that we're gonna have at 10, that represents what we see at 109, right? So is all of this clear to you guys so far? Are we all good?
Yes, Miss.
All right, Desharé, are we all good?
Yes, Miss.
All right, so let's move on to the other question now. All right, so the other question is saying now, deduce the formula of the M+ and the M+2 molecular ion species and name the haloalkane. So we did all of this already. So it's just a matter of bringing that down here, right? So let's go back up. Let's go back to what we had. So what did we have? So we have that our molecular ion, our M+, right, was this. So our M+ is C3H779Br. So let me just erase everything and write that now. So our molecular, so our M+, right, was C3H7Br79, right? This is 79 bromine. And then the M+2 now would have been C3H7Br81, right? And so if we're supposed to name the haloalkane, let's draw it out again. It was C, so H. So this is H, a H here, 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 and then we have the bromine here, right? So we would call this 1 bromo, 1, 2, 3, 1 bromo propane, okay? So that's 1 bromo propane. That's our haloalkane. Okay, guys, so this is our final answer. So let's box that here. This is our final answer. 1 bromopropane is what we got from that mass spec. That's our answer. So how are we with this, guys? How was that?
Good, Miss.
All right, Desharé, how was that for you? And did you do this on your own, both of you?
Miss, it
Yes,
was
Miss.
good for me. I didn't do it on my own though.
What was that?
I thought I'm saying I didn't do it on my own, but I understand. I'm just not sure if I'd be able to figure this out. Like if I got it on the exam.
Yeah, you just have to practice, right? And just remember the key things, right? Like you are asking a clarifying question on how did we know that that was the molecular ion peak? I hope that that was clear for you. I hope that the M+2 stuff is clear for you as well. That you know that will arise if we have a halogen that has isotopes. And the other key point is that to look at the relative abundance, right, of the M+ peak and the M+2 peak. And really and truly, what the rest of it is, it's just a lot of math, right? Once you figure out what your halogen is, if you're working with a haloalkane, then you will know that the remaining ones are just carbon and hydrogens. And of course, you can just divide out by the mass of the carbon to figure out how many carbons you have, and whatever is left over is hydrogen, and just kind of work from there, you know? And just know that these other things on the graph are fragments, right? Which means that the molecule is broken in different places. And that's why we see these ones. This is our most stable fragment. So this would be like formed like from like a tertiary carbocation would give you a super stable fragment, right? So you can just think of that. And then I think it should be good, but I would say nothing beats more practice, right? So definitely go ahead and practice some more mass spec questions from previous past papers and just get comfortable with the type of spectrums that CAPE give, okay? So that's what I would say. But if you were able to follow clearly what we just did, I think you should have a solid understanding of how to